In this video, we're going to talk about the derivative of an inverse function. And there's a lot that goes into inverse functions, but we're going to specifically focus on taking the derivative of an inverse function. So in terms of our content, finding the inverse of a function is going to be less important to us. That's really a pre-calculus topic, and we're going to take a look at some of the definitions and guidelines and things like that, but we're really going to focus on finding the derivative of an inverse function. And there is a nice algorithm for that we are going to use and look at a couple of different examples as well. So, the definition of an inverse function, essentially the definition, I'll read this first and then I'll kind of explain how simple it really is. But a function g is the inverse function of the function f if f of g of x equals x for each x in the domain of g and g of f of x equals x for each x in the domain of f. Basically what that's saying is the x values in the f function are the y values in the g function. So the x and the y switch. And that is really as simple as it is, but that is the definition of an inverse function. I kind of like Theorem 5.6 better. It talks about the reflective property of inverse functions, and it says that the graph of f contains a point a, b, if and only if the graph of f inverse contains a point b, a. So again, the x's and the y's switch. And that's kind of the simplest way to think about what inverse functions are. The existence of an inverse function tells us that not every function has an inverse function. A function has an inverse function if and only if it is 1 to 1, and if f is strictly monotonic on its entire domain, then it's 1 to 1 and therefore has an inverse function. One of the easiest tests that we can use to determine whether a function has an inverse is the horizontal line test. It is similar to the vertical line test that tells us whether something is a function or not, except instead of using a vertical line, we use a horizontal line. So if we were to look at, say, a parabola opening up or down would fail the horizontal line test, because a horizontal line would not go through only one point. It would go through 2 points on most places on the graph. Therefore, quadratic functions do not have inverses for that exact reason. Again, that's a review of things that come from pre-calculus, but something that you should be aware of. Guidelines for finding an inverse. This is something that you did extensively in pre-calculus. Gives you the step-by-step, but essentially you switch x and y around and then solve for y, and once you do that, your new function is your inverse. We're not going to be doing that. Instead, we're going to focus on this rule right here, the derivative of an inverse function. So if you are asked to take the derivative of an inverse function, that can be done by taking 1 over the derivative of the inverse function. We're not going to specifically do it just for a function. We are going to do it for a function at a point. That way we can find the derivative of an inverse function at a point, and that tells us the slope of the inverse function at that point. So this algorithm right here can be found on the curriculum map in the Learning Target section, as well as in the Chapter 5 review. You can see it right down here. We've got the derivative of an inverse function, and there is the algorithm. So how do you do this? Well, these questions are almost always going to require a calculator, and on the bottom here is an example. So given the function f of x equals 1/4 x to the third plus x minus 1, let's go ahead and find the derivative of the inverse of that function at 3. Now the thing you have to remember is that 3 there represents 3 on the inverse function, not on the function itself. So we can't just take 3 and substitute it in for x. Instead, we have to ask ourselves what y value on our function is represented by the x value, because we have to take the inverse. So the question we're really asking ourselves is highlighted right here. F inverse of 3 equals what? Now, I already know the answer is 2, but how did I get that? Well, essentially what I said to myself was this. F inverse, whoops, not F prime, let's erase that. F inverse of 3 equals what? How do I find that? 3 in the inverse function here is really a y value in the function. So I wanted to know, where does my function 1/4 x to the third plus x minus 1 equal 3? If I wanted to know where this function equals 3, I can graph it on my graphing calculator, and I can find out where the function equals 3, and the easiest way to do that is to graph the function 1/4 x to the third power plus x minus 1. And I'm going to graph that in the standard window. And where does this function's y value equal 3? Well, it's somewhere in here. And if I want to find out exactly where that somewhere is, I can go on my equations and make the equation y equals 3 so that it shows me the horizontal line y equals 3. And now if I can find the intersection, it'll tell me the x value where that happens. Now it appears that that happens at x equals 2, but we can confirm that by hitting second, trace, intersect. Make sure that your cursor is just to the left of the intersection point, just in case there's multiple intersections. And when I hit enter for the first curve, enter for the second curve, and then guess, it tells me the intersection is at the point 2, 3. Keep in mind though, we're talking about the inverse function. So when y is 3, x is 2, which is where we get f inverse of 3 equals 2, because in the inverse the x and the y switch. Now how does that help us? Well, if I scroll down here, the work that I just put in blue is written here, and then I actually did it a little differently in my scanned in solution here. What I did was subtract the 3 over, and I found the 0. So I graphed the function 1/4 x to the third plus x minus 4, and since it was equal to 0, I found where it crossed the x-axis. Just to show you that real quick, I'm going to go back to my function, and I'm going to change this to 1/4 x to the third plus x minus 4. I no longer need y equals 3, and when I graph this, it's going to cross the x-axis in one place. If I wanted to confirm where that was, I would hit second trace 0, and I need left and right bounds. I'm just going to manually type in 1 for my left bound, 3 for my right bound, so that it blocks off where it crosses the x-axis. And when I hit enter, it tells me that the 0 is x equals 2. So there are a couple of ways you can find out what the x value is that you're looking for. Once we find out that x equals 2 is the value that we need, then we have to take the derivative of our function and evaluate it at 2. And keep in mind that 2 is not an x value from our original function, it's actually the y value, and I think I just said that backwards. It's the x value from our original function, but because we're doing the inverse, it's the y value of our inverse function. So we need to find f prime. Easy to do. 3 times 1/4 is 3/4. Drop down to the second power. So that's where we get 3/4 x squared. Derivative of x is just 1, and the derivative of -1, of course, is 0. But then we're going to evaluate the derivative at the x value we found earlier. So we're going to substitute 2 in. 2 squared is 4. 4 times 3/4 is 3. 3 plus 1 is 4. And that is the value that we're looking for. So if we go back to the algorithm if you want to find the derivative of an inverse, you need to find 1 over the derivative of the inverse at that value. So f inverse of 3 equals 2 because on our original function, when y is 3, x is 2. So f inverse of 3 becomes 2, and then f prime of 2 we got from the function by taking the derivative and then evaluating at 2. Since f prime of 2 is 4, our answer is 1/4. A little bit complicated process, but once you get the hang of it, it's pretty simple. So let's look at one more example of this. Given the function f of x equals x to the third plus 2x minus 1, let's find f inverse, the derivative, of the inverse at 2. So we have to start by first asking ourselves not what is f of 2, but what x value makes our function equal to 2. So f inverse of 2 equals 1. Where did that come from? Well, if I wanted to know where f inverse of 2 equals 1, I'm really asking myself, where does my function equal 1? Where does my function, where does my function equal 2? Where does my function equal 2? Two ways I could do that. I could either graph x cubed plus 2x minus 1, and then make the horizontal line y equals 2. And when I graph this, here comes my function. There's y equals 2. Second, trace, intersect. And I'm to the left of my intersection point. So when I hit enter, 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 I find out that y equals 2 when x equals 1. I could have also done what I did in my notes here, which is subtract the 2 over and graph the function x cubed plus 2x minus 3. Oh, looks like my calculator just froze on me. So I'm going to bypass that here. If I were to do that, I would have been able to find the 0 of the function instead. And either way you do it, you're going to find out that x equals 1. Once we know that x equals 1 is the x value that makes our function equal to 2, we can now use the inverse to finish the problem. So we need to find what is f prime at 1. So f prime is pretty easy, 3x squared plus 2. And then we evaluate that at 1. So 1 squared is 1, times 3 is 3, plus 2 is 5. And then to finish, we use the algorithm. So if we want to find the derivative of the inverse of 2, we need to find 1 over f prime of the inverse of 2. F inverse of 2 came from us graphing the function and finding out where is y equal to 2. Y was equal to 2 when x was 1. So f inverse of 2 is 1. Therefore, we need to find f prime of 1. F prime of 1 was 5, so our answer is 1/5. This is a process that we use to find the derivative of an inverse. It is one of the topics that certainly could be tested on the AP Calculus AB exam.